Here's a picture from a lovely website, thispersondoesnotexist.com. As the name of the website suggests, these are fake people generated by a computer. It's a random generator and it gives a different face each time you run it. So how do we generate faces like this? This is what's called unsupervised learning. We're given a dataset, in this case a dataset of faces from Flickr, and we want to be able to generate new values similar to those in the dataset. We don't want to just slavishly copy what's there, we want to generate novel values, but we want them to be broadly similar. This specific goal is called generative modeling. There are other tasks we might want to do. For example, we might want to discover clusters in the dataset. I'm not going to go into those other tasks. Basically, once we've solved the generative modeling task, all the others will just drop out. What makes this tricky is that the dataset is unlabeled. It's just a mass of unlabeled data, so we can't use the conventional machine learning approach of minimized prediction loss. There isn't anything for us to predict. So how on earth should we evaluate it? Is there any sense at all in which we could keep back some holdout data and test our neural network's performance on that holdout data? What would we be comparing it to? You could imagine some sort of human-in-the-loop evaluation. In other words, take some machine-generated faces, ask the human to evaluate them. Or, better, take some machine-generated faces and some holdout faces and then ask the human which one looks more genuine and hope that the human can't tell. This is pretty useless. It doesn't scale. It's not really machine learning if we need human input every step of the way. Or we could be cleverer. We could imagine training a second discriminator neural network to do the evaluation. We'd show it the synthetic faces and our holdout faces and see if it can tell the difference. This is a very powerful idea. It's the basis for generative adversarial networks, but it's very hard to get right. Did our generator do well because it's a good generator? Or did it seem to do well just because the discriminator we trained was inadequate? But there's another way to look at this problem, which sidesteps all of this muddle. It's the probabilists approach. What we'll do is we'll model the dataset as a collection of independent samples from a random variable, call it x, and we'll try to fit our distribution to the dataset we're given. But we want to harness the power of neural networks. There's no neural network here, it's just a random variable. Neural networks are things for taking inputs and doing lots of processing to produce an output. So where's the input-output problem in this task? There's an almost embarrassingly simple trick. We'll just declare, I want my random variable x to be generated using a neural network. I'll feed in some exogenous random input z, which I'll generate using an off-the-shelf standard random number generator, for example uniform of 0, 1, and I'll task my neural network with transforming z into an interesting output x, whether it's a face or a piece of text or whatever it is I want to model. Then it's obvious how to train the neural network. This is just a probability model, and we can train the probability model using maximum likelihood estimation. And how do we evaluate our model? The answer is actually really simple, and we'll come to it in a moment after seeing an example of training. Here's my example. We're given a dataset of points x1 up to xn, points in R squared, and we want to train a generative neural network model. These points are actually a sample of pixels from one of the images in the MNIST dataset. The question tells us what type of model it wants. It asks for a model of the form f of z plus noise, where z is uniform and f traces out a path in R squared. Here's the sort of path we might expect. If we can learn the function f, we've learnt the pen stroke that might have been behind this digit. Of course, the points don't lie precisely on this line, so we're looking for a probability model. The probability model that the question specifies says x is f of z plus noise. In other words, we pick a random z which measures the distance along the path, and then we jitter it randomly, a normal offset in both coordinates, to get an actual data point. This induces a probability model, i.e. a likelihood function over R squared. The likelihood depends on the noise parameter sigma, and we'll want to estimate sigma as well as f. Now, probability modeling is always exactly the same. We first write out the log likelihood of the entire dataset. Here, I'm modelling my dataset as independent samples, so the log likelihood is the sum of the likelihoods of each of the individual data points. The formula for the log likelihood of a single data point x is a little bit tricky. We generate x by first generating z, so let's expand using the law of total probability, conditioning on all the possible values that z might take. The question was actually set up quite carefully to make it easy for us to do this. The question told us that z is a discrete random variable, a discretized version of the uniform. We'd really prefer z to be a continuous uniform random variable, but it takes more advanced math to deal with that, and we'll come to that in later videos. Here, z is discrete, so this probability is a nice simple finite sum. And then the rest is just mechanical. I know the conditional distribution of x given z is just a simple normal, so I can write out the log likelihood function explicitly. And now that I have an explicit log likelihood, I can just maximize it in the usual way, using PyTorch and gradient descent. There's nothing clever going on here. What's clever is that we've been able to turn learn how to synthesize new random values into an optimization problem. Once we've written it as an optimization problem, it's easy to just crank up the machine learning machinery. Here's a nice quote by Andrej Karpathy, director of AI at Tesla. "Gradient descent can write code better than you. I'm sorry." The job of us humans is to turn our machine learning tasks into optimization problems. In the case of unsupervised learning, it takes maths and probability skill to figure out how to do this. But once we've got an optimization problem, we just hand it over to the computer, problem solved. Let's go back to the problem we set ourselves. We set ourselves the task of synthesizing new values that are similar but not identical to the training dataset. Do we achieve this? Well, yes. The points we generate, if we plot them, give us exactly the likelihood function, of course. That's what the likelihood function is. If our likelihood function is smooth and nice and puts probability mass in the right place, then we've done what we set out to do. In this case, by eye, it looks good. But how should we evaluate it numerically? How can we come up with a metric for measuring whether our points are similar but not identical to the training dataset? The answer is staring us in the face. If we just do the normal machine learning trick of splitting the dataset into training and holdout sets, and if we fit the model on the training set, then we can measure the log likelihood of our holdout data points, the points in red. If we've overfitted, then we've assigned a very high likelihood to all of the training points, but the likelihood for the holdout points will be very low. In other words, our neural network has learnt to regurgitate the dataset we gave it. It can't produce anything novel. And if we've underfitted, then there's probability mass all over the place, but because likelihood has to integrate to 1, the likelihood has to be small everywhere, and so the likelihood of the holdout points will again be low. In other words, our neural network hasn't learnt the shape of the dataset we want to model. Let's summarize where we've gotten to. In unsupervised learning, we're given a dataset and we want to learn to synthesize new values that are similar but not identical. A better way to put this is, we want to fit a probability model to the dataset. We want to harness the power of neural networks, so we'll choose what's called a latent variable probability model, one that starts with a latent or hidden random variable z and then transforms it to get the output we want, x. Once we've decided on this model, then it's easy to train and to evaluate. It's just log likelihood all the way. So that's the message. Neural networks should be thought of as probability models. Training a generative model is just plain maximum likelihood estimation, trying to maximize the log likelihood of the training set. And log likelihood is the evaluation metric too. It measures how good we are at generating novel values, and it also at the same time measures how good we are at generating values similar to the training dataset. And what's more, it's exactly the same evaluation metric that we use for supervised learning. Probabilistic neural networks are really the simplest thing we can possibly imagine. Once we've set up a likelihood function, everything else is just cranking the handle. Now, I told a white lie. At the beginning of this video, I showed you pictures of randomly generated faces. These were generated from a latent variable probability model of the sort we've been discussing, but they weren't trained using maximum likelihood estimation. For all the calculations we've been doing, all the training and evaluation, we need to be able to write out the log likelihood function. But for interesting random variables, it turns out that this is actually rather tricky, and we'll need much more advanced probability machinery to be able to proceed, as we'll see in the following videos.